Okie dokie. So here we are, week 3, part 1, where we're talking about systems of equations. So we are refreshing our memories on solving by substitution and elimination, and then we're taking a look at the graphs of these things and sort of relating that to what kinds of solutions we end up with. So for our first example, we have two equations. Notice we have two equations, two variables, so that's called a system. Two equations, two variables, or we're going to be dealing with three equations and three variables. Oh yeah. So system of equations. And this asks us to solve all three ways. So let's take a look at what happens when we graph, first of all. What I've done is I've taken each of these equations and I have solved for y, meaning I got y all by itself on one side by subtracting 2x from both sides here, and by adding y and then subtracting 1, so two steps from both sides here. So we have a slope on y-intercept and a slope on y-intercept, and in blue and orange I'm going to graph those. So looks like this. In blue we have a y-intercept of 4 and a slope of -2, so down 2 over 1 like this. In orange we have a y-intercept of -1, a slope of 3, so we go up 3 over 1, up 3 over 1, etc. The place where these cross is the one point that they have in common, meaning the x comma y that both of those equations share, or the x comma y that works in both of the equations. So we get x equals 1, y equals 2 as the solution of that system. So you might want to write that there, solution of system, x comma y. Let's see what happens when we solve by substitution. So the idea behind substitution is we have this equation, the 3x minus y equals 1, and then the other equation in blue, I'm going to do this for a second. Alright, so here are our original two equations, 3x minus y equals 1. So that's here. You see, instead of y, I took y from the other equation and substituted in the -2x plus 4. So it's color-coded for you there. We have this original equation in black and the first original equation resolved in blue for y. So y has been replaced in this equation, and combining like terms, dividing, etc. gives us x equals 1. Once you have that, you still need to figure out what y is. You can use either of the original two equations or any form of that equation later on. So substituting in gives us that y equals 2. Notice how this is the same value we got down here in the graph. X equals 1, y equals 2. Okay, substitution. Now elimination is where instead of taking one equation and plugging it into the other, we basically take both equations. Sometimes we're going to multiply one of the equations by something, but we're going to add them together or we're going to subtract them. And do you see what happened here where this is pretty set up? We have a positive y and a negative y, so if we just add the equations together, plus y minus y gives us 0, and the y variable has been eliminated, meaning it has disappeared. So that's why we call this elimination. And so it's kind of a simple example. We just had to add the two equations together, but we end up with x equals 1. And then I plugged into one of the original equations, this one, to show you that either equation will work, and we end up with y equals 2. So all three of these techniques will work always. Sometimes one or the other will be a lot more work or less work than the other one, but as long as you don't make any math mistakes, you're going to end up with the same answer, and it can be expressed like this or as an ordered pair like this. Same thing. Let's take a look at page 2. Whoops. Let's take a look at number 2. Alright, here we go. So a similar situation. We have two equations. So this is a system of equations. Two equations, two variables. And we're going to solve using graphing. And then I think we have a choice in the second one. So what I've done is I've taken this part and I rearranged it so that y was all by itself. Alright, so added 2y, subtracted 6, and then divided both sides by 2. So it's now in slope-intercept form. We have y equals 2x minus 3. But take a look up here. This equation is also y equals 2x minus 3. Suspicious. So let's take a look at the graph. I think that this one is in, this one was in black and this one was in orange. All right. So we have 2x minus 3 in orange. Negative 3 is the y-intercept and a slope of 2. And then in black, negative 3 is the y-intercept and a slope of 2. So these lines overlap. And if you were asking yourself the question, where do they cross? Or where do they intersect? Well, the answer would be, that's right, everywhere. So this point is a solution to both of those equations. This point is a solution to both of those equations. This point is a solution to both of those equations. This point is a solution to both of those equations, etc. So what we say here is there is an infinite number of solutions. All right, so that was tricky. And what happens if we solve by elimination or substitution? So let's see, this top equation was all set up, y was all by itself, so that's a pretty setup for substitution. Here's the bottom equation, so I'm taking whatever y is and replacing y in the bottom equation with that. It's all color-coded for you. Distributing gives us this, and when we solve down, we end up with 6 equals 6. And I say, well, I'm pretty sure, yeah. 6 is always equal to 6, meaning no matter what x and y are, the equation is going to work. So this is an indication of infinite number of solutions. We will touch upon that on page 2. All right, infinite number of solutions. So that was number 2. Let us take a look at number 3. So here we have two equations, and what I did was skipped a couple steps, and we're putting this in slope-intercept form, and we're putting this in slope-intercept form. So dividing both sides by 2 yields this, and subtracting 2x and then dividing by 4 gives us this. So we have in blue negative 1/2 x plus 5, and in orange negative 1/2 x plus 4. Their graphs look like this. Y-intercept of 4, slope of negative 1/2, y-intercept of 5, slope of negative 1/2. And if you're asking yourself, where do these intersect or cross, these lines are parallel. They never cross. So these are parallel. So they never cross, never intersect. In this case, there would be no solution. There's no point that is on both lines because they never cross. And let's see what happens when we actually go to solve that. So we have a choice here, solve by elimination or substitution. And I think I chose substitution again. That's kind of my favorite, to be honest. So 2y equals negative x plus 10. What have we done? We, negative 10, okay. Added x and then subtracted 2y to get x all by itself so that we can replace x with that. So we're taking this, the negative 2y plus 10 in orange, and plugging it into the bottom equation. You can never substitute. If you substitute back into the same equation, you're going to get some jibber-jabber. So you always substitute into the other equation. So we have 2 times whatever x was, and then the rest of it. We distribute. Negative 4y plus 4y is nothing, and so we end up with 20 equals 16. What? And you're like, wait, math is lying to me. No, math is telling you something. And if the equations, after you combine them, tell you something that is not true, nope, I don't think that's ever true. It means there is no solution to that system. No matter what x and y are, 20 will never equal 16. All right, so in summary, how many solutions does the system have? This is what would we call this? Compare-contrast chart. How many solutions? So if it has one solution, the graph would look something like this. The lines will cross once. And when you solve down, you're going to end up with something like a variable equals a number, meaning that is a single solution, an answer. If there are an infinite number of solutions to the system, the lines will look something like this. They will overlap. And when you solve down, you're going to end up with something like a number equals itself. This is always true. And if there are no solutions, you will have parallel lines. They will never cross. And in solving, you'll end up with something like a number equals a different number that is never true. So, always true and never true. All right, and then just a brief little reminder here. So, flashback from Algebra 1, slope-intercept form, just in case. I know it's been a long summer. Not long enough, ha ha ha. So this is the slope and the y-intercept. For point-slope form, the thing that students tend to forget is that these, the x and y, are variables, meaning letters. The y1 and x1, these are numbers, meaning the coordinates of a point. I'm going to abbreviate here, coordinate of point. Any point on the line. And m, you know, is the slope. All right, point-slope form, standard. And then something that students tend to forget is, let's see, if we said x, I'm just going to tell you. So the y-intercept, if x were 0, we would have c over b. And if y were 0, we'd have for the x-intercept c over a. So thinking about the y-intercept and the x-intercept when you have the equation of a line in standard form tends to be very helpful. And then the slope formulas like that, we have rise over run, but you know that. So brief reminder, thanks for listening.